Okay, so the final talk of today's afternoon session will be by Dan Voiculescu. And I think the title was an exercise in free probability, the free Euler equations, if I'm not wrong. So please go ahead.
Okay, so I'm going to talk exactly about this, about how to set up some analog of the Euler equations in the free probability framework. And so a few words about free probability. It is a framework, a probabilistic framework for quantities with the highest degree of non-commutativity. The random variables are quantum mechanical, that is operators on Hilbert space, but the independence, the notion of independence on which this theory is built, is free independence, which is a modification of the definition of independence. It's different, it imitates free products in a sense, while the other one, the usual independence, imitates tensor products. And if we pass to free probability, the theory runs rather parallel to usual probability. There are analogs for lots of things in free probability. For instance, for the central limit theorem, the Gauss law is replaced by the semicircle law. And the theory has important connections with von Neumann algebras, combinatorics, random matrices, asymptotics of group representations. And this parallel between classical and free goes unexpectedly far, and actually it is still growing. There are still new additions to this parallel. I'm going to talk about this recent one, adding to the parallel an instance of Euler equations, equations of the flow of inviscid fluid. Now, this may seem very far, to go very far from hydrodynamics, to go over to such non-commuting quantities and to think of hydrodynamical situations in this context. But there is a precursor to all this. There is a paper by Bourret and Frisch called Parastochastics, where on other questions about fluids, by analogy, they introduced a lot of analogs of Gaussians, non-commutative analogs of Gaussians. You find there the beginning of the Q-deformed non-commutative Gaussians and such things. So going very non-commutative has been actually also on the mind of some people in fluid dynamics. So I'm going to use to get an analog of a certain Euler equations. It's a particular instance of Euler equations for which I have an analog in free probability. I am going to use as a recipe the Arnold approach to Euler equations. So in the Arnold approach, the ingredients are a Lie algebra G, a non-degenerate scalar product on the Lie algebra, and one has to find a bilinear form B from the linear algebra to the linear algebra, such that the following relation holds. The commutator of A and B scalar product with C should be this bilinear form applied to C and A, scalar product with B. And then the Euler equations are equations for maps of a time interval, 0t, to the Lie algebra. So for every time t, you have v of t, an element in the Lie algebra. And the equations are that the derivative, the time derivative of v is minus b v of t with v of t. There are some kind of geodesics equations which appear here. And the classical model, which for which I found a free probability analog, is the following situation: is the Euler equations preserving a Gaussian measure on Rn. So it's a very particular instance, and it's an instance which is probably not too much liked by people who do fluids. I mean, to take a Gaussian measure to be preserved, but still it's still Euler equations preserving a certain measures. When the group is a diffeomorphism group of Rn, and those diffeomorphisms which preserves a Gaussian measure. And the Lie algebra will be the vector fields on Rn which preserve this Gaussian measure. The bracket in the Lie algebra is minus the Poisson bracket, and the scalar product is this integral scalar product, Hilbertian scalar product, with respect to the Gaussian measure. We take the components of the field, U, the vector field U, and the vector field V, and it's the scalar product with respect to this Gaussian measure. And if one does this, it's easily looks at the Euler equations in this setting. Then, because one has this Gaussian measure around, everything can be interpreted probabilistically, namely the coordinate functions on Rn with the Gaussian measure form an n-tuple of centered IID Gaussian random variables, which I'm going to denote by x1 twiddle, xn twiddle. Then the vector fields which preserves the Gaussian measure are n-tuples of functions on Rn, good functions, I mean, it's infinity, whatever. We're going to go as far as to simplify things as to look at polynomials. And if one takes these infinitesimal increments to the random variables, so the Gaussian random variable xj twiddle is perturbed with epsilon, this function vj of x1 twiddle, xn twiddle, then this should have the same distribution as x1 twiddle up to xn twiddle, this n-tuple, up to order epsilon square. That means that there are increments which preserve infinitesimally the Gaussian measure. And the distribution, in order to make sense of this epsilon, order epsilon up to order epsilon square, it's good to look at the distribution as moments. So one takes, it's a collection of moments of this n-tuple of random variables, and these, as function of epsilon, don't change up to order of epsilon square. How does the free probability analogy go? So we have analogs of Gaussian random variables, and the Gaussian random variables, they live on a full Fock space. So the replacement for the L2 space of Rn with respect to the Gaussian measure will be the full Fock space on Cn. Yeah. So it's a tensor algebra of Cn with the scalar product, which is the Boltzmann-Fock space scalar product. X1 twiddle, Xn twiddle, the Gaussian random variables correspond to these left field operators. It is Lj is a creation operator on the left. So it's Xi goes to Ej tensor Xi, where E1, En is a basis, canonical basis in Cn. And then one has S1 is L1 plus L1 star, Sn is Ln plus Ln star. And the expectation functional is with respect to the vacuum vector, which is vector in the zeroth component of the tensor algebra. And one takes the expectation with respect to the vacuum. What happens is that these S1, Sn will be, in this free probability setting, will be freely independent, and they will have distributions with respect to the vacuum semicircle law. So this can be also modeled with random matrices, IID random matrices independent in the larger n limit. They behave exactly in the same way. And now the vector fields, the analog of the vector fields, which preserves the Gaussian measure infinitesimally, here it's complicated, I mean, to deal with very general increments. So we start and look at polynomial increments, non-commutative polynomials. And if I denote, so S1, Sn are the non-commutative Gaussians with n tuple of semicircular random variables. Sj plus epsilon, these polynomials Pj in S1, Sn. And these have moments with respect to the vacuum expectation. And one requires that the polynomials be such that up to order of epsilon squared, these moments should be the same. They change only higher order in epsilon, but the first order is no change. So these are the vector fields. These are the Gaussian random variables. And now let me say a few things about the differential calculus I'm going to use, because I need to have Poisson brackets. I need to have other things to write Euler equations. So in the free context, let's now take S1, Sn, use the same letters I put here for the for these free Gaussian variables. Let's take indeterminates, non-commuting indeterminates, and for the moment, make them just indeterminates. Later, I will at some moment go back and make them again operated. But for the moment, let's keep this S1, Sn indeterminates. And let's denote by this Cn here the non-commutative polynomials in these indeterminates S1, Sn. Then one has partial difference quotient derivations. It's they do the following thing. It's this del J, which when they see in a monomial Si1, Sip, when they see an Sj, they erase it and put a tensor. So it is actually, if you want, it is the derivation of Cn into Cn tensor Cn, which takes Sj to one tensor 1, and the other one's sk with k different from j takes them to 0. That's this derivation. And then there is another derivation. It's not a, so this is a derivation. It's a derivation because Cn tensor Cn is a Cn bimodule, and it is a derivation. There is another map which is called the cyclic derivative. It is not a derivation. It's the cyclic derivative, but it is related to derivations, but it's not a derivation. And it's a map from Cn to Cn. And what it does is it takes, you see, every time I see in a product Si1, Sip, every time I see an Sj, it moves it to the first position, cyclically to the first position, and erases it. It can be viewed also as the following thing. You take this partial difference quotient I've written above, and you move the right-hand side in front of the left. Yeah, you take Si1, Sik plus 1 Sip and put it in front here. Multiply the Si1, Sik to get this. So this is called the cyclic derivative, the partial cyclic derivative, the J with respect to Sj. Now, what role do these two derivatives play? One is a derivation, the other is only called a derivative. If I have a bimodule, a Cn bimodule, could be, for instance, von Neumann algebra generated by its elements, and I have B, an element in the bimodule, then I have a map MB, and such an insertion map from the tensor product of two copies of Cn to E, and simply takes Xi tensor eta and maps it to Xi B eta. It puts a B between Xi and theta instead of the tensor. Then if I use these insertion maps, I can define what would be vector fields, the analog of vector fields. Namely, I do the following thing. I take this partial, I start here with Cn, so that's the polynomials, these non-commutative polynomials, things of them as a caricature of functions, yeah, polynomials. And I'm taking the partial, this partial free difference quotient, and then I'm inserting, instead of the tensor there, I'm inserting the bj, yeah? And that gives me a derivation from Cn to this bimodule E. It is exactly the derivation which takes the indeterminates S1, Sn to B1, Bn. It is the unique derivation with this property. So if I take then if I give to S1, Sn such increments in the bimodule, S1 plus epsilon B1, Sn plus epsilon B1, and takes the derivative of the polynomial at epsilon 0, I'm getting exactly this kind of derivation applied to the polynomial P. So such a derivation in a bimodule applied to P, it's exactly by how much the polynomial changes if I first order, if I make these increments. The role of the cyclic derivative is when I do the same thing, but not with the polynomial, but with the trace of the polynomial. So I have on the algebra M where all this happens, I have a trace. And then I have S1, Sm, this is, I assume they live in M, and the B's also in M. So then I take the trace of a polynomial and I give to S1, Sn this infinitesimal increments, epsilon B1, epsilon Bn, and the derivative of the trace of the polynomial is exactly this Bj's trace of Bj times the cyclic derivative delta Jp. So you see, it's a function like what the gradient does in certain situations, this n-tuple delta 1 delta NP as a function like a gradient in this situation. And it will be called the cyclic gradient, will play an important role in what I have to say about Euler equations. The vector fields for Cn, this will be the Lie algebra, the analog of the Lie algebra of vector fields with minus the Poisson bracket, will be n copies of what are the functions of the polynomials. So it's Cn n power, so n has n components, yeah. And the Poisson bracket of two such non-commutative vector fields is defined exactly by the same kind of formula as usual Poisson bracket. Yeah, you take the derivation given by P, apply it to the components of the vector field Q, and minus the derivation defined by Q applied to the components of P. And then the brackets for the Lie bracket for the Lie algebra of vector fields will be minus the Poisson bracket. And we'll come now to define what would be the vector fields which preserve a certain measure. The vector fields which preserve a certain measure, the measure translates here into a trace. So I'm having a trace state on the functions. The functions are these non-commutative polynomials. So I'm having a trace state on the non-commutative polynomials. And there are the vector fields which preserve the trace tau infinitesimally. So these are such vector fields, so such n tuples in this case of polynomials, which have the property that the polynomials times the components of a cyclic gradient. So I'm taking R, another polynomial, and I'm taking its cyclic derivative, partial cyclic derivatives, and then I'm taking Pj delta Jr, these tau of this. It's like a scalar product, and this should give 0. So this is the analog of the divergence-free vector fields. And here you see the map from Cn, which takes a polynomial to this n tuple of partial cyclic gradient, cyclic derivatives, is natural to call it the cyclic gradient. And what happens is that the trace preserving vector fields are exactly the orthogonal of the cyclic gradients. Yeah, so it's what happens with the divergence-free vector fields also classically, but here you have the non-commutative situation. And to deal with cyclic gradients, I have found an exact sequence which goes as follows. I take these polynomials in the n non-commutative indeterminates, the Cn. I take the bracket, but here it's just commutators, A, B minus BA, yeah? Cn, and I add the identity. So this is a subspace in the polynomials, in the vector space of polynomials, non-commutative polynomials. Then from the non-commutative polynomials, I go over to the n components, that's the vector field Cn, with the cyclic gradient. And then I have here another map theta. This map theta takes P1 direct sum with Pn to the sum J of the commutators of the Pj's, the components, with the indeterminates. So it's sub Sj with Pj. And then what happens, this is an exact sequence. So we know that the range of the cyclic gradient is in the kernel of theta. And we have also other relations. We have that the image of the map theta, if you add the scalars, the multiples of the identity, you get the kernel of delta, and it is actually also equal to the kernel of a cyclization map, this map which when you have a monomial adds to it all its cyclic permutations, yeah, of the monomial. Now, so all this was about formal differential calculus. I had put the trace, but I did not use anything specifically about how these indeterminates S1, Sn are, what they are. Now let's make these indeterminates be non-commutative Gaussians, yeah, semicircular random variables, what we call in free probability. So let's take Sj is this Lj plus Lj star. So Lj is a left creation on this full Fock space. And the trace is given by the vacuum. Then what happens is that the von Neumann algebra generated by the Sj is isomorphic to the one factor of a free group, yeah, of a free group. And the map from L2 of the von Neumann algebra with respect to the trace. So it has this, the vacuum expectation gives a trace on this free group von Neumann algebra. And if we take the L2 space with respect to the trace, then the map which takes the L2 space to the full Fock space applied to the identity is a unitary operator. And what it does is it takes this product. You see, I have here SI1, SIM, different, so consecutive ones are different of these operators, of these SJs, yeah. So there can be the same can appear several times, but not consecutively. And I apply to them Chebyshev polynomials. Then this, when I apply it to one, I'm getting EI1 tensor K1, tensor EIM, tensor K. It is the same thing for the free case that you have in the what you would have in the Gaussian, classical Gaussian case, what you would have with Hermite polynomial. This is the stuff about Wick ordering and what it becomes in this free context. Here you have Chebyshev polynomials. And now I'm having a map from the vectors, the vector fields for Cn, yeah. Vector fields for Cn, this Cn is this non-commutative polynomials. The vector fields is just the nth power of this, so n components and such polynomials. I map them into L2 of this von Neumann algebra M tau, and it's a dense subset. And then I have the Euler projections, the analog of the Euler projection, which will be the orthogonal projection of the whole thing, the closure of the vector fields, onto the vector fields which preserves the measure infinitesimally, the divergence-free, the closure of divergence-free vector fields. And here is the moment to tell you why it's important for me to work in this Gaussian context, in this, why don't I make this consideration absolutely general? Because the Euler projection is very difficult to handle if I would have just some von Neumann algebra M and a generator S1, Sn, and self-adjoint elements which generate this von Neumann algebra, which has a trace. So you say a 2-1 factor and an n-tuple of self-adjoint elements which generate it. And then I construct all these things. I have absolutely no control over how big this closure of of trace preserving vector fields. Are there any? I don't know anything. But in this Gaussian context, in the context of semicircular random variables, something very useful happens. It is that the Euler projection works well with the gradings. It is you see, I have proved that the vector fields, these vector fields which preserve the trace, decompose orthogonally. It's a direct sum of orthogonal components in the various degrees. This is something which happens also in the classical Gaussian setting with Hermite polynomials for these Euler equations. You have the divergence-free vector fields. They also decompose orthogonally with respect to the causes. And the cyclic gradient has also such an orthogonal decomposition. And then you have orthogonal decompositions at each degree. So Cn tensor k, n tuples, every time you have decomposition xk plus yk. Xk is a component of the vector fields, and yk is of the trace preserving vector fields, and this is the cyclic gradients, yeah, this orthogonal decomposition. And the xk's can also be this degree k vector fields can be also described nicely with using left annihilation and minus right annihilation applied to elements from the higher order. So it's a very good algebraic situation that the things start splitting. This actually, without this orthogonal splitting, I could not have constructed this, made sense of these Euler equations. It is here is a key point that I have this orthogonal decomposition. And then if I apply just to the vector fields without the closure, the Euler projection, I'm getting then the trace preserving vector fields. If I take the orthogonal projection, I'm getting the space of cyclic gradients. Everything is nice. And one has to work more. I mean, one has to, all this was with complex, the complex Lie algebra. One has to work with the real Lie algebra, it's real vector fields. So one takes the self-adjoint elements. Everything works nicely. I don't bother you with this kind of details. What I need to mention is another of my older results, is that these vector fields, which are trace preserving, yeah, these trace preserving vector fields, the self-adjoint. So it's the n tuples of polynomials, and if I give these increments to S1, Sn, the trace is preserved infinitesimally. This is a derivation on a dense subalgebra of this von Neumann algebra, which is the von Neumann algebra of a free group. This derivation exponentiates to a one-parameter group of automorphism of M. One has to prove that, and it's non-trivial. So it exponentiates, and the exponential makes sense. So that's another feature of these vector fields, which makes these Euler equations possible. So what are now the Euler equations? For this, I need to go to the Arnold recipe. So the scalar product, it will be component-wise. It's this trace of AJ, BJ. That's like you had in the classical case. It was the integral of AJ, BJ. AJ, BJ is the components of the vector fields, and the integral with respect to the Gaussian measures. This, and here is a equation which gives this bilinear form B. So I need to have scalar product of the commutator AB with C. AB is a Lie bracket AB, and scalar product with C should be B, CA, comma B. Now this B, CA, it's fortunate, can be computed, and it is Lincei projection, and then this is applied to the derivation which corresponds to A. Yeah, has n components, so it is every Sj gets replaced by an Aj, applied to Ck, to the kth component. And here I have a sum. This is this insertion map. The twiddle is changes after the twiddle coming after a partial free difference quotient. It changes the order of the components, etc. Now, the nice thing is that if I put C equal A, this second term, which is more complicated, disappears. And it's just Lincei projection and derivation corresponding to A applied to the components of AK. So the Euler equations one gets, it's I have such a map V, which goes from a time interval, and it goes to this algebra of vector fields. They look exactly like like the classical ones. It's the derivative of V in time plus this Lincei projection, and here you have this, the dV applied to Vk equals 0. And the V's are required to be divergence free. So this is not an equation, this is written in a different way. What you would expect there, the divergence free condition is that actually that V is in this vector fields SA. And this can be also given this form without the Lincei projection, Vk dot plus dV Vk, and here you add a cyclic gradient. Yeah, it's a component of a cyclic gradient which get added. That's the other form of this Euler equations. Now, these Euler equations are for polynomials. That's not a very good class of functions. Fortunately, something nice happens again, because I'm in this good Gaussian situation. Namely, there is a subalgebra in the von Neumann algebra of smooth functions to which the equations can be extended. So the equations will make sense for the elements in this subalgebra. Now, this subalgebra are things like that, are elements in the von Neumann algebra, and you take these commutators with imaginary parts of the right creation operators, and these commutators should be trace class. These kind of conditions, that is smoothness spaces, defined by the fact that commutators with certain singular integrals, things like that, are in normed ideals in Schatten von Neumann classes. The beginning of the story, this is with the work of Feller on Hankel operators, and these spaces are connected to Besov spaces, therefore Hankel operators. So it's again this, what I've denoted here by B infinity comma 1 is a kind of non-commutative relative of some Besov kind of spaces. And it has this natural norm. This type of spaces with different free contexts has also played some role in certain questions about K-theory. And smooth algebras, yeah, work of Kohn, how he managed to find another proof for the absence of idempotence in the reduced C-star algebra of a free group using this smooth algebra. So this is B infinity comma 1 at I denote. And then I take B equals Bj n components in this B infinity comma 1. And what one can prove is that these derivations, which were these vector fields corresponding to B1, Bn, these derivations, they extend to this algebra B infinity comma 1. and they extend and they give operators affiliated to the von Neumann algebra, operators in L1 of M with respect to tau. So this is good, and one has such a precise inequality. And also the cyclic derivatives, they also extend with values in L1. So one gets unbounded operators, no longer, but one gets out of the von Neumann algebra. These are the affiliated operators of the von Neumann algebra. Also, the cyclization map, C, works nicely because it has, again, it's L1 norm, L1 MT. And the properties of DB, all these maps extend by continuity. But not to the, some of these, one cannot go to the this full algebra B infinity, comma 1. For certain things, one needs the closure of the polynomials in this algebra. So certain things one has to do in this smaller algebra than all this big Besov type algebra. And then it makes sense to consider the Euler equations for functions with values in this algebra B infinity, comma 1. So this the Lincei projection does not work on this B infinity, comma 1, but again, the fact that the Euler that the Lincei projection projects onto something which is nicely graded is of help. So one can take components. One can take k order components, which are finite rank maps, and with these check that one has divergence, so to say, divergence-free vector fields. So these equations minus v dot t, p, etc., when v is in B infinity, the v takes values in B infinity 1, can be defined. One can make sense of these equations, but one has to be careful that since the P is not defined, this Lincei projection is not defined on this L1 space, but one can only use these finite rank things, the kth order, the pk, and with the pk's one gets such a, instead of one equation, one set of equations, one gets a sequence of equations in each degree. But there is in this way a way to make sense of the Euler equations and to check that things are all right. Now, one other thing is that I was able to find also that there is something like vorticity for these three Euler equations. Namely, classically, to get to vorticity, one applies the curl and kills the pressure term because it's a gradient. So applies the curl to the gradient, and that's how one gets to vorticity. For the three Euler equations, there was this exact sequence I had found. You see this exact sequence here, this exact sequence, which has this map theta, some SGPJ, some commutator SGPJ, which kills the cyclic gradients. Yeah, you have this delta, the cyclic gradient, and theta. And so one can play the game which one plays classically with using the curl to get rid of the pressure term. One can play it here with this map theta, applied to the equations which have been written with pressure term. And what one gets this cyclic vorticity. Now, the cyclic vorticity is the sum of commutators. It's I times Sk, this commutator with Vk of t, Sk Vk of t. And one has a cyclic vorticity equation minus the time derivative of omega is the dv of t, omega of t. So this is in the b infinity, comma 1 context. So for solutions in b infinity, comma 1, one has such vorticity equations. And what happens is that there are, like in the case of classical vorticity, there are additional equations. There are these equations which give how the vortices, the evolution, but there are also these equations like you have that the divergence of the curl is 0, things like that. There are these equations, the cyclization map applied to omega t is 0, and tau of the trace of omega t is 0. So the additional equations for the vorticity equation are that cyclization of omega t is 0 and tau of omega t is 0. But here, this is no longer in B infinity 1. This is in this subalgebra, the closure in B infinity 1 of the polynomials. And one gets conserved quantities. The conserved quantities are the powers of the vorticity, the trace of the powers of the vorticity. The whole distribution of the vorticity is actually conserved. It follows, this is a consequence of the vorticity equation. And the vorticity equation has this consequence. And in general, if I take a function of the vorticity, of the trace of this function of the vorticity of any Borel function is preserved. And I have to make some additional remarks. One may wonder what is the replacement for boundary conditions in this situation. The boundary conditions, a natural thing would be to require that these vector fields, dt, they define derivations. These derivations defined on dense subalgebra of the for Neumann algebra M, and one has to require that this would extend to one parameter groups of automorphisms. The fact that these densely defined derivations on the von Neumann algebra extend to one give rise to extend these derivations are infinitesimal generators of one parameter groups of automorphisms. That's the replacement of the boundary conditions. One can imagine also some free Navier-Stokes equations. The candidate would be to add an additional term, which would be some function of the number operator in this Boltzmann-Fock space. That would be kind of viscosity, but that's unexplored. Now let me say something about the references. So there is my paper, or this hydrodynamic exercise in free probability, setting up free Euler equations. It has appeared in Exposiciones, and it's also available on arXiv. There's an older paper of mine, cyclomorphy in International Mathematics Research Notices, where I found these properties of the algebra of trace preserving vector fields, this orthogonal decomposition is there. And there is this other, a short note in Indiana Math Journal about the exact sequence for cyclic gradients. There is now some quite recent work by others. There is a paper by Tobias May and Roland Speicher, which has appeared in the Journal of Operator Theory, and it's also on arXiv. It's quite recent, and it's somehow working continues what I did in this note on cyclic gradients, where I had the exact sequence. They have more things in this direction, and then there is a big paper by Jekyll, Lee, and Shlachtenko, which was put very recently on the arXiv. And they construct a free Wasserstein manifold, and they find a way to arrive to this kind of Euler equations you've seen here from the point of view of this free Wasserstein manifold, and somehow to develop things which would bring it close to transportation situation, work with transportation methods on these equations. So I should say, I mean, this last paper is also a new addition to this parallel of free and classical. We're having now also a free Wasserstein manifold, which would clarify in particular also this Euler equations. So this is what I had to say.
Okay, so thank you very much for this interesting talk, and I again invite questions from the audience. So if at the moment no one has a question, I would ask one, namely, you mentioned this possibility to go also to the Navier-Stokes equation, and I was wondering, can you also have something like an analog of the Onsager conjecture for this kind of change of behavior when you consider weak solutions to the Euler equations, that there is some kind of turbulence already there?
I don't know.
Okay. Okay. So let me have a look if
I don't know.
There's one question from the audience.
So you discussed the free probability case. So what about, for example, other Fock space like the anticommutative?
I mean, the situation is the following. So the classical one, the Gaussian, is bosonic Fock space.
Yes,
so
and what about the fermionic one?
The fermionic, well, I mean, if you think about the fermionic, that's a finite dimensional thing. This is some kind of rigid body in the Clifford setting, something like that. I don't know that it's been done, but that's what it looks like. It's kind of rigid body in a Clifford setting.
Yeah, okay. Then one could imagine, because then there are, so a related question maybe, in Arnold's book, there are also finite dimensional approximation to Euler, no?
Yes,
which are this generalized rigid body, if I remember correctly.
Yes, well, that's very difficult.
Okay.
I don't know for the free to have approximations.
I think, okay, thanks.
So are there any further questions? So if not at the moment, let me have a look whether there's a question online. So it doesn't seem to be the case at the moment. So yeah, then let's thank the speaker again, and maybe also all the other speakers. I think we resume tomorrow at 10 again. So thanks, everyone.